My name is Steph Brener, and I'm a bioengineering PhD student at UCSF. My background is in medical devices and the development of electronic olfaction. I am currently working with Dr. Simon Little in the Movement Disorders and Bioengineering Department at UCSF. Our research focuses on decoding neural biomarkers of mood and motivation to develop novel, closed-loop neurostimulation therapies for Parkinson's disease. Parkinson's disease can cause mood and motivation disorders, although more commonly known for its motor symptoms, such as slowness, rigidity, and rest tremor. On top of that, there is often a great deal of apathy, depression, and anxiety that co-occurs in Parkinson's disease. The first line of defense is normally taking dopaminergic medication, but this can often lead to novel problems like dyskinesias on the motor side and impulse control disorders on the non-motor side, including gambling and sex addictions. My research focuses on the non-motor symptoms of Parkinson's disease, specifically the impulse control disorders, and on the opposite side of the spectrum, apathy and issues with motivation. Parkinson's disease functions by degenerating the frontal deep brain networks involved in decision-making. And one therapy that can treat this is deep brain stimulation, which is used in advanced Parkinson's disease. This delivers electronic stimulation to the deep brain structures that are degenerating in the condition. Now, one way that we can understand decision-making in the brain is by recording neural data using non-invasive EEG, which records brain data from the scalp, as well as implanted deep brain stimulation electrodes recording brain data from those deep brain networks. And by simultaneously taking these recordings, we can understand the interplay between these two regions of the brain deeply involved in healthy motivation and decision-making tasks. If we combine this with a particular task that participants can see in the lab, we can now probe specific moments in a decision-making pipeline. In this case, it's an example of a gambling task where participants have to make cost-benefit trade-offs between whether they are willing to win a certain amount of points for a certain amount of risk. The goal of this work is to eventually develop novel adaptive deep brain stimulation therapies which can treat mood and motivation disorders. This is currently a style of therapy which is approved for treating motor symptoms, where you can increase and decrease stimulation depending on how bad a certain symptom is detected to be in the brain. And although this works great for motor symptoms, it's not currently in play for non-motor symptoms. The research that I am doing, if we find these particular multivariate neural biomarkers that indicate healthy decision-making versus unhealthy decision-making, and we can track those over time, you can increase and decrease stimulation to better treat that symptom as opposed to constantly delivering the same stimulation all day. I want to give a big thanks to the ARCS Foundation for helping to fund this research and all of their support that they have provided throughout. Thank you.